In this lesson, we'll be looking at the relationship between electrons and light. At first, light seems simple. We see it every day, or at least we use it to see every day. But when scientists began studying it closely, they discovered that light behaves in some very unexpected ways. In some situations, light behaves like a wave, helping explain color and interference. In other situations, it behaves as if it comes in tiny packets of energy. By the end of this lesson, you should be able to describe how light and matter can display the behavior of both waves and particles. So I'm going to show you some examples of different things giving off different colors of light. I typically show this to my students and ask them to identify what the common theme is and to distinguish between them, but that doesn't really make any sense in this case. So we're going to go ahead. So here we have some white light being given off, some more white, some white and blue light. So hopefully you have enough experience with things to know that, well, we probably have some different elements present. And then we got, looks like white, blue, and pink. That pink color is one of my favorites. It's characteristic of lithium. And then we got an orange color. That's characteristic of calcium. Some more red-orange. And now we're going to switch to something other than fireworks. So here you have some light being generated by thermal excitation. So we got, looks like some calcium. Let me turn my thing on. Calcium, that looks like lithium to me, the flame color, and this is barium. Got some flame tests. Typically when people do units on light and electrons, they will be doing a flame test lab where you will get to do this yourself. One of the learning objectives for a lot of states is that students understand that the color that is given off by a, quote, neon sign is due to the gas that's present inside. It's not due to coloring of the glass or anything like that. So if you fill one of these arc discharge lamps with helium gas, you get a white-yellow color. Neon is that characteristic red that we associate with neon signs. Argon is purple. Krypton is green. And xenon is blue. This is probably my favorite one. So you can see all of these things are generating different colors of light. And what's causing this is the movement of electrons from higher energy levels to lower energy levels. All right, so we're done with the pictures. So now let's do a little bit on definitions. So the wavelength is defined here. Hopefully you've already seen this in a class like physical science. So the way you measure a wavelength is you go typically from crest to crest, the top of the wave. You can go from trough to trough. Oh, that doesn't work on this. There we go, an orange one, trough to trough. The important part is that you're going from one repeating point to the next repeating point. You can see as we go from red wavelengths, and this has been drawn with the appropriate colors to show you the illustration between wavelength and color. As you go from red, which is a really long wavelength, to violet, you have much shorter wavelengths. So the shorter the wavelength, the higher the frequency. The symbol we use for wavelength is lambda. Looks kind of like a wave coming into shore. If you imagine it's breaking off to the left. And then the higher the frequency, and we use a Greek letter nu for frequency in chemistry. In physics, they use an F. In chemistry, we use a nu because, number one, Greek letters are cool, and number two, F means something else in chemistry. So frequency, let's define that. So frequency is the number of waves that can go past a point of time every second. So if we look at the long wavelength, we'll just say this represents a 1 second worth of time, and the waves are propagating that way. So we have only like maybe a quarter of a wave managed to travel past that reference point in 1 second. So this has a very low frequency. If you come down here to the violet, we have 1, 2, 3.5 waves, no, 4, excuse me. waves went past that reference point in 1 second. So violet has a much higher frequency. So yeah, the longer the wavelength, the higher the frequency. And the thing that bothers people a lot, especially if they've done any kind of studying in physical science, you know that if you have a mechanical wave, you have bigger the amplitude or the intensity of the wave, the more energy it's going to slam you with, like especially if you're talking about ocean waves. Light doesn't work that way. The energy of the wave depends only on the frequency of it. And so, like I said, this gives people a lot of trouble. So I have a little illustration of this. So it's the same diagram. And so we're going to pretend that we can actually ride on these waves just like if they were water waves. So here we are in a red wave. The red wave is moving up and down very slowly. We have a nice gentle movement of the boat. So now we're going to put it down onto the green wave, and now we've got a bit more energy in that motion, moving up and down with a greater frequency. And if you notice, my little guy is looking a little green from all this motion. And then let's put him next wave down. I couldn't fit it onto the violet waves for some reason. And so now the water's really choppy. We're going up and down with a lot of energy. And there's so much energy in this case that we knock the guy right out of the boat. So hopefully that will help you remember long wavelengths, low frequency, low energy. Short wavelengths, high frequency, high energy. All right, so here is kind of a typical electromagnetic spectrum. Hopefully you remember that the visible light spectrum is only a very small part of the total electromagnetic spectrum. If you notice, it just kind of doesn't have any more lines past gamma rays, and that's because they don't really have any way to observe or measure the wavelengths that are shorter than gamma. And likewise for AM radio waves, we're already talking about something that's like 10 kilometers long. So again, it's kind of hard to talk about it in terms of anything new past AM radio. All right, so remembering that red is the longest wavelength, we know that as we go this way, come down here, this way, the wavelength is getting longer and longer, and energy is getting lower and lower. And so if we go to infrared, that's even lower. So as we go all the way out here to AM, we have super long wavelengths and very low energy. If you go the other way, so now we're going out past violet. So infra actually means below, and ultra means above. So we go above or beyond violet. So now we're in ultraviolet rays. So we have shorter wavelengths, higher energy. This is why you want to wear sunscreen when you go out, because those ultraviolet rays have enough energy to cause skin cancer. They cause scrambling of your DNA in your skin. So you want to protect yourself. And then we go to X-rays. Again, you don't want to have overexposure to X-rays, gamma rays, and so on. All right, so life isn't worth living if you can't do a little bit of calculation or do some math. So one of the things you can do is you can convert between wavelength and frequency using the handy-dandy equation that's shown right here, where the speed of light, which is 3 times 10 to the 8th, it's a constant, that's why it's c, is equal to the wavelength times the frequency. So just an example, what's the frequency of a 400 nanometer wave? Now this is where you got to be careful with your units. The speed of light is in terms of meters per second, so that means we have to convert our nanometers into meters. One of the real handy shortcuts is wherever you see a nano, put in a times 10 to the minus 9. And then just like punch it into the calculator and hit equals, and it will do the conversion for you. So this ends up being 4 times 10 to the minus 7 after you hit equals. And then we're looking for frequency, so frequency is going to be equal to the speed of light divided by the wavelength, all in the appropriate units. And we get that it is 7.5 times 10 to the 14th hertz. So there's a couple of different units for this. We have hertz, which is the easiest to type. We also have seconds to the -1, or reciprocal seconds, or cycles per second. is actually where the seconds, reciprocal seconds come from. I almost always use hertz because it is the least confusing out of all of them and it's the easiest one to type. All right, so here we have our hydrogen 1 atom, 1 proton, 1 electron. So so we have the 1 energy level. Just because we only have the 1 electron, it doesn't mean there aren't other energy levels. They just don't have any electrons in them. All right, so we got our electrons traveling around the nucleus, nice regular fashion. And we're going to use the Bohr model for this because it's a lot easier to work with. And then we have some light energy comes in. If it is a single wavelength or frequency of energy, it's called a photon. It's like a packet of energy. So if that electron gets hit with exactly the right amount of energy, it'll be excited and it'll jump up to a higher energy level. So the lowest energy level is called the ground state, and that'll come up in a minute. And if you're above that ground state, you're in an excited state. It's kind of like you're running around the track and then a dog that's foaming at the mouth starts chasing after you. You're going to go into an excited state. You're going to start traveling a lot faster. So eventually the electron is going to give that energy back off. So if you take energy in, it is absorbed. If you give it back off, it is emitted. And this electron went back to the ground state. And that is, like I said, the lowest possible energy level. So the key thing here is to understand that when we see all those pretty colors and the light being given off, that's the result of excited electrons dropping down into lower energy levels, because we can't see energy being absorbed. We can only see it when it's being emitted, and our eyes can actually detect it. All right, so here is the atomic emission spectrum for hydrogen. This has all the possible different transitions between the different energy levels for that 1 electron. And remember, the Bohr model could only really worked for hydrogen or hydrogen-like atoms. And that's because if you have multiple electrons, they start interfering with each other. So for this series in here, where we're going between the first energy level and anything else, they are all ultraviolet transitions. So we see that we have super short wavelengths. And then if you go from the second energy level and out, between any of the other ones that are farther out than the second one, then that is where the visible light comes from. And then if you go from the third energy level out, that is the infrared. So here is an atomic emission spectrum of hydrogen. And we can see that we have 1, 2, 3, 4 fairly bright lines. And if you notice, there are 1, 2, 3, 4 emission lines in the hydrogen spectrum that was drawn up there in the Balmer series. So remember, red is the longest wavelength. So that means that this red line corresponds to 656 nanometers. This bright blue line corresponds to 486 nanometers. We have this slightly not as brilliant line, which is 434 nanometers, and then this very faint one, which is 410 nanometers. Now, it doesn't mean that the number of electrons that are going between the different energy levels, the second and the fifth, second and the sixth, there's any less frequency to it. They have probably the same intensity, but when we look at different things, look at light, our eyes are not very sensitive to the violet end of the spectrum. So while these lines are probably just as bright as these other two lines, it's going to look like they're dimmer. So just some more examples. So here's potassium. It has a real pretty lavender, pinky purple kind of color. It's got a whole bunch of lines down in the blue. I was always kind of surprised by the fact that it doesn't have anything in the red. You would think for purple it would need to have some red. And then we got barium. It's got a bunch of red and green, and that's because with light you end up red and green make yellow. It's the way light works. And then calcium is the orangey pink one. It gets used in fireworks quite a bit because it's cheap. And then lithium is that hot pink color that I told you I liked. All right, so like I said, if light is being given off, that means an electron is dropping from a higher energy level to a lower energy level. So if you know the frequency, there's one equation, but there's two different versions of it, depending on whether you have frequency or wavelength. So if the frequency is known, then you can find the energy of that particular photon, or the energy of that light that's being given off, using this equation right here, which is energy is equal to a constant, it's called Planck's constant, times the frequency. So H is always going to be this number down here, 6.626 times 10 to the negative 34th. Don't worry about that dot in between the joules and the seconds. That confuses my students all the time. Just focus in on the number. And so the example is if we have a frequency of 1.2 times 10 to the 14th hertz, what is the energy? So we just plug the numbers in. There's Planck's constant times the frequency, and we get an energy of 7.95 times 10 to the minus 20 joules. If you have wavelength instead of frequency, you can either convert it using the speed of light is equal to wavelength times frequency, or you can use this form of the energy equation. It just does the conversion for you. And so you have a wavelength of 780 nanometers, so that's like a dark red. So that means you put it in the calculator, change the nano to times 10 to the negative 9, and you get 7.8 times 10 to the minus 7 meters. What is energy? So now it's going to be Planck's constant times the speed of light divided by that wavelength in meters, and we get an energy of 2.55 times 10 to the minus 19 joules. Notice that energies are very small, frequencies are huge, and wavelengths tend to be kind of in between the two of them. All right, just so some more examples kind of going back and forth between the different equations. If the energy of a green photon having wavelength of 504, well, what is the energy if your wavelength is 514 nanometers? So we got that, just plug in the numbers, and we get an energy of 3.87 times 10 to the minus 19 joules. What is the frequency? So I wouldn't be converting it back using this calculated value. I would use the conversion using C is equal to lambda times frequency, or wavelength times frequency. You don't want to use a calculated value to calculate another value, because then if the first one's wrong, the second one's going to be wrong too. And so we get a frequency of 5.84 times 10 to the 14th hertz. And it says, what is the frequency of a photon that has the energy of 3.31 times 10 to the minus 27 joules? All right, so notice that the green photon, visible light, is 10 to the minus 19 joules. So this is an even longer wavelength than green. It's times 10 to the minus 27. So we should end up with a much longer number. So we solve for frequency. Now we're doing it in terms of hertz. Okay, we end up with 5 times 10 to the 6 hertz, so 5 megahertz. So that's down like in microwave range. All right, so strange behavior of light. I have a much longer presentation than I do in class, but I'm going to keep it a little bit briefer here. So he says, hi, I'm a photon. Some people say he has a dual personality. So as I said, one of the learning objectives is for you to understand that both matter and light can behave as though they have both wave natures or behavior and particle natures. So here we have a photon, which is when you have light behaving like a particle, is typically how photon is used. So the dual personality, the idea is that how something behaves depends on how you're looking at it, how you're perceiving, depends on your perception. So the first one, I have a whole bunch of these optical illusions. I ask my students, how many legs does the elephant have? Invariably, I'll have a student say 4, and I say, well, that's what you think, regular elephants do, but does this elephant have 4? And so the answers I've gotten over the years is anywhere from 1 leg, which I think they mean this one because this is the only one where the leg is attached to the foot, to 8, I think is the maximum number. This one is the old lady, young lady image. So we have, it depends on how you're looking at it. And it's funny, if it depends on which one you see first. So if you see the old lady first, it's going to be really hard for you to see the young lady, and vice versa. So let's see, let's do the old lady first. The old lady has a great big nose, and she's kind of looking over here to the bottom left-hand corner. There's an eye. She's got bags under her eyes. She's got a wart on her nose, and she's kind of frowning. That's her mouth. The young lady is looking off over her shoulder, kind of off towards the mid-left part of the screen. There's her nose peeking out. This is her jawline. There's her ear, and she's wearing a red choker. And then the last one that I'm going to do, there's only one image in here. And again, it depends on, I think it depends a lot on your experience as far as what you see in this one. I've had people tell me they see skeletons or skulls, and I think it's because of this pattern over here in the corner. Occasionally, it is a cow. And occasionally I will have people identify that it's a cow, but they're looking at a different part of it. So in case you don't see a cow, here's an ear. It's got a black ear. There's another ear. There's an eye. There's the other eye. Here's its nostrils. And there's like the bridge of its nose. So yeah, electrons and photons, how they behave depends on how you're perceiving it. All right, so the wave nature of light, the way they justify saying that light has a wave nature, is if you have a planar wave coming in. So if we're looking at this picture, just imagine that the white lines are the crests, and then these red lines or these red areas correspond to the troughs. And so we have a whole bunch of waves kind of coming in like this. They hit the barrier. There's only 2 very small openings. Those small openings cause diffraction of the light of the wave, and so we end up getting bending of the wave. And so now we have constructive and destructive interference, and you end up generating an interference pattern where the dark lines correspond to where they cancel each other out, and the bright lines correspond to where they added constructively. This is just the same diagram, but it's animated, so you can sort of see how the waves are traveling and how you get that crossing of the different radially distributed waves. Excuse me. All right, photoelectric effect. This was first observed in 1887 by Heinrich Hertz. And let me explain what the photoelectric effect is. So they found that if you take a source of light and you bounce it off of some kind of metal, they tend to use a lot of alkali metals for this, that it would come in as light, but it would result in the ejection of electrons. And these electrons are sometimes called photoelectrons. They had a hard time understanding what was going on with this. Because at this point, physics was dominated by classical wave theory, which described light as an electromagnetic wave. Early attempts to explain the photoelectric effect assumed that light transferred energy in a continuous fashion. So you get little bit, it keeps on increasing. You don't have any steps. If this was true, photoelectrons would be ejected from the surface if the light was bright enough. Instead, what they found was that below a certain frequency, no electrons are emitted at all, no matter how bright the light was. Above that frequency, electrons were emitted immediately and did not depend on the intensity of the light. So it was only the frequency that determined whether electrons would be ejected. And then increasing the brightness increased the number of photoelectrons, but not their energy. All right, so let's go on to the next part. So in 1905, Einstein proposes something really radical, that light itself is behaving like individual particles, and this is what we now call photons. This was an enormous conceptual leap as he was questioning a core assumption of classical physics, that energy can be divided endlessly into smaller and smaller amounts, the continuous spectrum. Each photon, Einstein argued, carries a fixed amount of energy proportional to its frequency. This means that one photon interacts with one electron. This was a key piece of the puzzle that Einstein was trying to solve. Suddenly, all the strange experimental results made sense. So they researchers, Millikan mostly, then investigated. Einstein's idea was not accepted immediately. And actually, Millikan was attempting to disprove Einstein's theory. Rather than disproving it, Millikan's incredibly careful experiment showed a perfectly linear relationship between frequency of the light and kinetic energy of the emitted electrons, exactly as Einstein had predicted. Ironically, even though he was trying to disprove the theory, Millikan's work provided some of the strongest experimental evidence for Einstein's theory. We had kind of an interlude where we didn't make a whole lot of progress because of World War I. And then by 1921, enough people were convinced that Einstein was right that he was awarded the Nobel Prize in Physics. Not for relativity, which is what he's probably more well known for, but for explaining the photoelectric effect. Keep in mind that the Nobel Prize is only awarded when a scientific discovery has been thoroughly tested, confirmed, and shown to fundamentally change how we understand nature. The long delay between Einstein's paper and the Nobel Prize wasn't a failure on his part or a weakness in his theory. It was evidence of careful application of the scientific method, tying it back to what we've been talking about. All right, so a little bit later, this is 1924, so 3 years after Einstein got the Nobel Prize, there was a PhD student who said to himself, if light can have characteristics of both particles and waves, can particles of matter also behave like waves? And this is more for enrichment than anything else, just to show you the power of wondering about things. So he based his entire doctoral dissertation on this. The guy's name was Broglie, and they were eventually able to obtain some experimental evidence that, yeah, electrons also behave like waves and particles. So the equation is the wavelength of the matter, so the wavelength of the particle, is going to be equal to Planck's constant, which we've already seen, divided by the momentum of that particle, so mass times velocity. So just to give you an idea of what these numbers look like, if you're talking about an electron, has a really small mass, it's moving pretty fast, not quite the speed of light, but it's pretty fast. And you end up with a wavelength that is about the same size as a neon atom. And it was actually electron diffraction is what they used in order to prove or verify de Broglie's equation. If we kind of step it up, let's talk about a golf ball, because that's probably a little bit more familiar to most people. You go and you drive it, or whatever you do with golf balls, down the green, and has a velocity of about 70 meters per second. It has a wavelength that is incredibly small. So you can see, just once we start talking about real objects, yeah, they can have a wavelength, but it's not going to be something you can perceive. And just to go to the totally ridiculous end of the spectrum, The Earth would have a wavelength of 4 times 10 to the minus 63 meters. They don't even have names for that unit as far as I know. All right, so the wrap up for this lesson on light. Light is a form of electromagnetic radiation and can be described by its wavelength, which remember we're going to use the symbol lambda, frequency, nu, and energy, and capital E. Shorter wavelengths correspond to higher frequencies and higher energies. Just think about the little guy in the boat. Excited atoms emit light at specific wavelengths, producing unique emission spectra for each element. And it should be excited electrons. Light exhibits both wave behavior, and we saw that with the interference patterns and diffraction, and particle behavior. That's where it's behaving like photons with the photoelectric effect. The photoelectric effect shows that light transfers energy in discrete packets called photons, not continuously. And then the idea of wave-particle duality leads naturally to the question, can matter also behave like waves? And it certainly does, at least when you're talking about something small like an electron. Okay, so that's it for this lesson. Thanks for listening.